Welcome to this edition of Lakeside Physics. We will be exploring the topic of friction, a force we couldn't move about without. There are two main types of friction. The first that we'll talk about is static friction. Static friction applies when an object does not move relative to the surface of another object, while a force attempts to move one of the objects relative to the other. Static friction opposes this attempted motion. Here is a basic example. Evan is trying to push the couch, but he cannot move the couch initially. The force that is opposing his motion to keep the couch at rest is static friction. The second type of friction is kinetic or sliding friction. This applies when an object slides across a surface. Kinetic friction always opposes the motion, so if an object is moving to the right, kinetic friction acts to the left. Let's go back to the video of Evan attempting to move the couch. As soon as he starts moving the couch, kinetic friction applies. So what does this frictional force depend on? At a microscopic level, it can get pretty complicated. We're going to be taking a simple model, though, that depends on really only two things. You may think it might depend on temperature or the speed of an object, possibly the surface area. Turns out it only depends on two things. The first is pretty obvious, the two types of surfaces. For example, if I try to move a box across the room, it depends both on the material that the floor is made of and the material that the box is made of. The second thing the frictional force depends on is the normal force. Now, this is related to the weight, but it is not equal to the weight. Now, here is an example where my son is trying to push a box across the room. In both cases, the mass of the box is the same, but the normal force is different. And when the normal force is large, it is very difficult for him to move. So here's the equation for static friction. The static frictional force will always be less than or equal to the coefficient of static friction times the normal force. Note that the static frictional force and the normal force are both measured in newtons. The coefficient of static friction has no units. The coefficient of static friction is what brings in the two types of surfaces. Alright, so let's do a little mini experiment. We want to find the coefficient of static friction between the block and the table pictured below. For this, we will use a spring scale to measure the force of which I pull, and we will slowly begin to pull it until we see the block just begin to move. Let's see below. So here I am. I start to pull it. I'm pulling 6, 10, 14, 16, and then the thing starts moving. So the force at which I just pull when it just starts to move is 16 newtons. That will be equal to the maximum static frictional force. So let's solve for the coefficient of static friction. Let's always start by drawing a free body diagram. We've got our force of gravity pointing down, our normal force pointing up, my pull off to the right, and then the force of static friction to the left. Note that if this is going to be at rest, then the net forces acting on the object need to sum up to 0. So, whether if I pull with 5 newtons, the force of static friction should be 5 newtons. If I pull with 10 newtons, it should be 10 newtons. If I pull with 12 newtons, it should be 12 newtons. Since it doesn't move, both the vertical direction forces need to add up and the horizontal forces need to add up. So the normal force is equal to Fg, and their force of static friction is equal to the force of the pull. Now, we saw from the video that the max I could pull with before the thing started to move was 16 newtons. Now I can use this max pull in the equation for static friction, that the force of static friction is always equal to or less than the coefficient of friction times the normal force. So in this case, our maximum static friction was the 16 newtons, and we can use this to help solve for this coefficient of static friction. First, we need to find the normal force. Since our normal force is equal to Fg, I was given, you guys didn't realize this, but the mass of the little block that I was pulling with, it had some other masses on it, was 3.3 kilograms. So our normal force is mass times g, or 3.3 times 10, giving us 33 newtons. So then we can solve for the coefficient of static friction by taking this maximum static frictional force divided by the normal force, or 16 newtons divided by 33 newtons. When we solve this, we get 0.48. So the experimentally determined value for the coefficient of static friction between the block and the table in the video is 0.48. Now let's consider the equation for kinetic friction. It looks very similar to the equation for static friction, except instead of having a less than or equal to sign, we just have that the kinetic frictional force is equal to the coefficient of kinetic friction times the normal force. Again, both forces are measured in newtons and the coefficient of kinetic friction has no units. The coefficient of kinetic friction is dependent on the two surfaces, but one thing to note is that the kinetic frictional force and the static frictional force coefficients are not necessarily the same for any given two materials. Often it'll be harder to get moving initially. The coefficient of static friction may be bigger than the coefficient of kinetic friction. Alright, so let's continue our mini experiment and find the coefficient of kinetic friction between the block and the table. So to find the coefficient of kinetic friction, I'm again going to use the spring scale, and I'm going to pull it, and once the block starts moving, if it's moving at a constant velocity, my pull should be equal to the force of kinetic friction. So I pull, I get it moving, note that it drops down and then hovers somewhere between kind of 12 and 14. It looks like it's about 14 there. So we'll assume that the force that I need to pull it at a constant velocity is 14 newtons. Alright, so let's go ahead and solve for the coefficient of kinetic friction. Let's begin by writing down the information that we know. We know it's moving at a constant velocity, and we pulled with a force of about 14 newtons when we were pulling at this constant velocity. We also know that the mass of the object is 3.3 kilograms, and we can go ahead and draw our free body diagram. We have the force of gravity down, normal force up, our force of the pull to the right, and the force of kinetic friction to the left. Since it's moving at a constant velocity, we know that the net force needs to be equal to 0. So this tells us that the force of the pull has to be equal to the force of kinetic friction, and the force of normal has to be equal to the force of gravity, which we already determined to be 33 newtons from our previous solving of the static friction. So we can go ahead and solve for we've got the force of kinetic friction has to be equal to coefficient times the normal force, or the coefficient is the ratio of the frictional force divided by the normal force, which is equal to our 14 newtons over the 33 newtons. And when we solve this, we get 0.42. So if we go back to our previous results, we found that the coefficient of static friction was 0.48, while the coefficient of kinetic friction was 0.42. Let's finish up with a couple of example problems. For the first one, we have a 2-kilogram book that is at rest on a table. A force of 5.0 newtons is applied horizontally to the right in an attempt to get the box moving, but the box does not move. Find the frictional force acting on the object. The coefficient of static friction is 0.5. If we begin with a free body diagram, we have our force of gravity down, our normal force up, applied force to the right, and the force of static friction to the left. Since it doesn't move, the net force must be equal to 0, so our applied force is just equal to our frictional force, and we get that the frictional force is 5.0 newtons to the left. Now, in that particular case, we did not use the fact that the equation for the static frictional force was mu sub s times Fn, because it only applies when you're looking at the maximum static frictional force. In this case, now, we want to find the maximum horizontal force that could be applied before the box starts moving. So, we can use this equation we know that the normal force will be 20 newtons in this case, and so we can take the coefficient of static friction times the normal force, 0.5 times 20 newtons, to give us a 10 newtons would be the maximum that static friction could apply, and so therefore it's the maximum applied force before the object will start moving. So let's do another problem. In this case, we have a 40 kilogram box is being pushed with a horizontal force across the carpet with a constant velocity. The coefficient of kinetic friction between the box and the carpet is 0.5. Find the force of the push. Again, let's draw a free body diagram. Looks pretty similar to our other ones. And we know it's moving at a constant velocity, so our acceleration should be equal to 0. Therefore, our net force is 0. This looks very similar to the example that we did with the block moving at a constant velocity. Our push is equal to the force of kinetic friction, and kinetic friction is mu k times Fn. Again, we can find that our normal force in this case, it doesn't always equal, but in this case our normal force is equal to the weight, which is 400 newtons, and we can then take our coefficient times the 400 newtons to give us 200 newtons. So if our frictional force is 200 newtons and we're moving at a constant velocity, then that must be equal to the force of my push, but to the right. So I have 200 newtons in the direction of the motion. Let's do one more example. A 5 kilogram box is pushed across a table with a horizontal force of 30 newtons. The coefficient of kinetic friction between the box and the table is 0.40. Find the acceleration of the box. Again, I'll draw a free body diagram here. This time our push is actually probably going to be bigger than our kinetic frictional force. So they're not equal in this case because we do have acceleration. We can again find our normal force is just 50 newtons in this case, and we are given that our push was 30 newtons and the coefficient of kinetic friction was 0.4. So our frictional force is 0.4 times the 50 newtons, or 20 newtons. So we can look at the net force must be equal to the mass times the acceleration. So our push minus the frictional force should be equal to the mass times the acceleration. So our push was 30 newtons minus the force of friction of 20 newtons should be equal to ma. So we get, when we solve this, that our acceleration is equal to 2.0 meters per second squared. So quick summary here, we found that there are two types of friction, static friction and kinetic friction. We use static friction when the object does not move relative to the surface, and it is only as big as it needs to be. So we have the equation that has this less than or equals to sign. Be careful, it's a common mistake to just solve for the static frictional force and use it in a problem when what you may be solving for is the maximum, and at a particular point in time it doesn't actually apply the maximum static frictional force. Kinetic friction is used when an object is sliding across a surface. Frictional force depends on two things, two surfaces, which comes about in the terms of the coefficient of friction, and the normal force. As always, let us know if you have any questions. Thanks.